Hello everyone, we're ready to start. On the menu today, we'll finish the MAC layer and start the transport layer. Let's start with a small quiz about the maximum packet size on Ethernet. I close in 5 seconds. The correct answer is probably E. I say probably. So the long story is, yes, there is a maximum packet size on Ethernet, which by default on all systems is 1500 bytes. That means if you create an Ethernet adapter in your startup company, you have to support packets of 1500 bytes. There are adapters, there are switches that support longer packet sizes, but it's not guaranteed that this will work. So in practice today, the only thing you can be sure of is that if you create an Ethernet packet of 1500 bytes, that will not cause problems. If the packet is larger and the switches on the way do not support such a large packet size, then your packet will be too large and will be dropped. We might wonder why there is such a limit. I mean, why don't we take any packet size? Like, why is not the correct answer G? Any clue? Stack Overflow, which means look for the solution on Stack Overflow? Or? Stack or buffer overflow, yes. You need somehow to put a limit on the size of packets that come into switches, for example, because they will have to queue them internally. If the packets can be 1 gigabyte, for example, then probably a large number of switches will have a problem. So you need to agree on some maximum packet size. This agreement was done very, very long ago. It was done in the end of the 70s, and the agreement was 1500 bytes. Then, as usual, that's a theme we will see in networking. Once something has been agreed in the lower layers of networking, it's very hard to change it. So the only practical packet size we will have today is this one. Let me jump to the addressing part of Ethernet that we have seen to a large extent already. So we know that with Ethernet, there is the concept of MAC addresses, MAC layer in general. And the original mental model was this one. It was a broadcast medium. And we put the destination packet address in the packet, and all the systems that are supposed to receive it analyze this address. And if it's yours, if it's their address, they take it. Of course, if we have a bridge rather than a shared medium system, then we have seen that the bridge needs to look up in its forwarding table to see what to do with this address. There are special addresses for multicast and broadcast. Broadcast is very specific to LAN, so we find it a lot at the MAC layer. As we know, the broadcast MAC address is all ones, which in the way we write usually MAC addresses gives this string, all Fs. And the semantic is, if you send something to this address, then all adapters in the network are supposed to receive it. If the network is a network of bridges, which is the common case for wired networks, of course we don't broadcast it on all links, but only on a tree, a subset of all links that does not have loops. So here this is showing an example of a broadcast packet sent by this device here. It will be received by the first switch. The switch will repeat it on all the ports that are not disabled. So this one it's disabled at this end, so it probably will not be broadcast, so that the packet will be broadcast everywhere along the spanning tree. The spanning tree guarantees that there's no loop. If there would be loop, what would happen? or the broadcast would circulate forever, so the packet would circulate forever. Is there a TTL in Ethernet? No. If we remember the slide last week of the packet format for Ethernet, there's no TTL. Since those are only bridges, if we broadcast something in a loop, then it will circulate forever. Nothing will stop it. The IP TTL will not be decremented because this is all a single LAN here. So it's as if A and all the systems were all on the same cable. So this is another reason for having trees in networks of bridges. It's for the broadcast because there is no way to manipulate packets to avoid circulating packets. Broadcast is used extensively. The theory says that we should prefer multicast to broadcast. So there are also multicast addresses that are used in Ethernet. Essentially two, multicast used for IP multicast and multicast MAC addresses that are used for IPv6 multicast. There are also special protocols like PTP that uses multicast, predefined multicast addresses for this protocol, MAC addresses. The rule of MAC addressing is that there is one bit that identifies whether it's a multicast address, and in the original, it was the first bit in the original format, but now bits were for some reason flipped because of differences between Motorola processors and Intel processors at that time. The long story short is that now it's bit number 8 when we write in the standard way, starting from the highest order bit on the left. Bit number 8 equal to 1 means it's a multicast address. So if we look at this address here, 0, 1, 0 is the first hexadecimal digit, 1 is the second one. If I write this in binary, there are zeros everywhere in the first 7 bits, and the 8th bit is a 1, so it is a multicast address. Same for 3, 3, because the representation of 3 in binary is 0, 1, 0, 1, so the 8th bit is a 1, etc. If it's an IPv4 multicast address, the meaning is if there is an IPv4 multicast address, then the packet will not be sent to the MAC broadcast address, but will be sent to a multicast MAC address that will be of this form. It means this packet will have 24 bits that are derived from the IPv4 multicast address, and the rule is very simple. You take the lower order 24 bits of the IPv4 destination multicast address, and you put them into the last 24 bits of the MAC address. And the same for IPv6, almost the same. Now we take here 32 bits instead of 24. Why we have different things here is not entirely clear, but this is how things are done. I should mention that what happens if there is a multicast address, where if you're on a shared medium, Ethernet or Wi-Fi, for example, probably it's broadcast. I mean, it's sent to everyone. So but with the destination MAC address, which is one of those. But physically, it will be sent to everyone. If you have a bridge network, or a network that's made of switches, now it depends whether your switches are smart or not. If you have Cisco switches that are expensive and smart, they will manipulate, they will truly handle the multicast well, in the sense that they will try to guess what are the devices that need to receive this multicast packet. For example, if multicast is used for distributing an audio stream or a video stream, there is an IP layer protocol that we will see very soon that is used to know whether a certain device is subscribing to this stream and therefore needs to receive the multicast address. Then such switches at layer 2 will overhear what happens at layer 3 and try to detect whether a given machine, like this one, is listening to the group. If so, they will build a distribution tree here. This is in complete violation of all architectural principles because we are imposing some functions at layer 2 that are derived from layer 3. Less sophisticated switches do the thing right. They are at layer 2. They have no mechanism to know which device belongs to which multicast group. So what they usually do is they broadcast it over the spanning tree. With the destination address, that's multicast, but the packet is physically broadcast. Here is an example that we have seen when we do acquisition of an IPv6 address. This is a Wireshark or a TCP dump copied from an IPv6 packet when one host is trying to acquire an address by sending a multicast to its solicited node multicast address. Now we observe the IPv6 destination address. We observe also the destination MAC address. And then the question is, what can you say about the way this multicast MAC address has been computed? I close in 5 seconds. Closing. Trying to close. Oh, it is closed. Voila. And the correct answer is the majority one, is answer C. It's a bit contorted, that's why we have a look at it, at least in this example in detail. There's a mixture of rules at the IP layer, how you build the solicited node multicast address from a target IPv6 address. That's one set of things. That is not the topic now. Another set of things is how you create a MAC multicast address from an IP multicast address. And if it's IPv6, you take the last 32 bits. You add to the prefix 3333. And the rest is how we go from hexa to binary, or from hexa the IPv6 way to hexa the MAC way. So the IPv6 destination address is this one. We need to take the last 32 bits, which corresponds to 2 words of 4 hexadecimal digits. So it is this block here, corresponds to 32-bit. Now, if I remove the compression, it gives this. And if I write it the MAC way, MAC addresses are typically written by groups of 8 bits rather than 16 like IPv6, so that gives this. I close in 5 seconds. And the correct answer is, of course, it gives us the IP layer protocol. So it tells us whether the data packet is an IPv4 packet or not. Whether it's a TCP packet or not, we will not see in the MAC header. We will see that in the IP header. Last question. We move from IPv4 to IPv6. Ignore multicast for a second. What do we need to change in the switches? I close in 5 seconds. The correct answer is A. Nothing, because the bridges don't look at the IP headers. At least as long as they don't try to do sophisticated support for multicast. If we ignore this thing, which can always be solved by broadcasting all the multicast frames, then the bridges are truly transparent to the higher layers, which is a very interesting thing today. It's very important. That means if you introduce IPv6, that means you do not have to change the bridges. So bridges and switches are typically the hardware infrastructure of a network, whereas IPv6 is in the software. So changing the software does not here impact the hardware, which is good news. It's not always the case. I mean, sometimes you buy a new camera, you need to change your operating system just to support it. Here that will not happen. And that's one of the reasons probably the MAC layer continues to exist And because when we move from IPv4 to IPv6, then we don't need to change any of the cabling and Wi-Fi infrastructure. So the story we've seen today is that of the MAC layer in its simplest form. In enterprise environments, there is another layer of complexity which is good or bad. It's probably bad, but is very popular. It's deployed practically in every enterprise. It's called virtual LANs. Here we find the extreme logic of the old way the TCP-IP architecture was built. TCP-IP was built with the idea that you have local area networks that are interconnected by an internetworking layer, which is the IP layer. And those local area networks were typically based on cabling or whether you are on the same Wi-Fi access point or not. For example, when you join EPFL in the morning, your mobile device connects to the first Wi-Fi base station of EPFL it finds, gets an IP address with DHCP from there, and belongs to a subnet, which is the subnet of the region where this Wi-Fi base station is. If you move, you go to CE2, which is at the other end of or CM2, which is at the other end of the campus, then you move with your mobile device, then you are no longer in the area where the Wi-Fi antenna is. What should happen? Well, the theory says what should happen. We should do mobile IP. We should do a handover where we keep perhaps the same IP address, but we have a mechanism to know that you are not in the area where you're supposed to be. It's the same problem you have with mobile phones. If you have a Swiss mobile phone, you go to another country, then you need to have a handover mechanism to know that you're somewhere else. Another way to solve it is with virtual LANs. That's the way that is solved by the infrastructure that is mostly deployed. Will consist in saying, well, I will extend the local area network where you originally registered to wherever you are. So if you move to this place and you're registered at BC, then you will still be in the same local area network, but in the form of a virtual LAN. So virtual LAN is illustrated here. It is the concept that you can have switches all along a certain network, and devices that are on the same switch infrastructure may be decided to belong to different local area networks. So here we have, for example, on the same switch, we have the red and the green devices that belong to different local area networks. The original motivation was not that of mobility that I gave now, but it was separation of devices. For example, this is a network that's used for accounting. This is one that's used for secretaries to type documents. And this is one that's used for engineers to do simulations. You want those things to be different for whatever reason. The reasons are typically security, avoiding broadcast storms and things of that nature. That are probably not really correct today. If you just rely on virtual LANs for security, probably you have very weak security. But that is an argument that's given. Very often you also have programs that will check whether, in order for C to be able to do a transaction with D, they will check whether you are on the same subnet. That's a weak form of security. So those are the goals. And originally, when the LANs were created, things were very static. The engineering department is not supposed to be in the same office as the accounting department, so you would wire the system such that people in one floor belong to one LAN, in another floor they belong to another LAN. Of course, this is not very flexible, and if you want more modern space allocation, you want to decouple the local area network you belong to from the physical place where you are. That's the requirement posed on this problem. Again, I insist that this requirement is arguable. We might say, what's the point of being in a given LAN for doing a given job, right? That assumes that the router infrastructure is not able to manipulate traffic that would come from different LANs, which is not true today. But if we accept those requirements, then we have to satisfy this solution, find a solution. How is the solution? Well, it consists in adding to the Ethernet header a field which is called a VLAN tag. I say added, it's not really adding, we are in fact reusing a field. In this field, in principle, we have the packet length. And, sorry, if the packet length is at most a certain number, 1500 bytes or a bit more for some other LANs, but if we find here a number that is much, much larger than any reasonable packet length, then it means it's not a packet length, but it's something else. It's a tag of some kind. Various tags have been defined. We will later see one of them called MPLS. Here, one tag is the virtual LAN. And the virtual LAN tag essentially consists in having a prefix of 16 bits, and that says this is a virtual LAN, and a LAN number, a virtual LAN number. So there's one number for the red, one number for the green, one number for the blue. And all these tags are typically not inserted in the station, so most end devices don't bother putting tags because they don't know which virtual LAN they belong to. But the switch, if it's an intelligent switch, this switch knows which virtual LAN this port belongs to. So the assumption here is that there is a switch management application in the background that has decided that this port, which corresponds to the socket in a given room, belongs to the red virtual LAN, whereas that one belongs to the green one. So this network management application has done the choice. When you receive a packet on this port, then the switch will automatically add the virtual LAN tag to the Ethernet header so that it will be considered a green packet. And then the rule is, if it comes from A, sorry. The rule is that communication can occur at the MAC layer only within a certain virtual LAN. In other words, if A sends a packet to Y with the MAC address of Y, then it will work because the switch here will add the green virtual LAN label to the packets coming from A, and then they will be forwarded by the switch or the network of switches as green packets. In particular, there will be one green spanning tree, one red spanning tree, and one blue spanning tree. So the bridges, the virtual LAN bridges, will build as many spanning trees as there are virtual LANs. For example, here between the two blue switches, the two switches that know of the blue LAN, they will forward the packet from B to X, but they will not forward a packet from B to A, for example, because the virtual LAN tag that comes here is green, and this is completely invisible to the blue packets. So to make it short, virtual LANs are really manipulated as separate networks, separate local area networks. Different virtual LAN labels correspond to different spanning tree, different forwarding tables also. A switch that has a forwarding table here, a blue forwarding table for those four things. It knows nothing of the green MAC addresses. So those two switches have no entry for the green MAC addresses in the forwarding table. If they would need to, they would have a separate forwarding table that would be for the green one. So it's intellectually very simple. Of course, it doesn't scale to zillions of virtual LANs. You're supposed to have a number of virtual LANs, that is perhaps a few hundreds, but not much more. But this is typical of enterprise environments. Last quiz on this topic. What will the A do in the case explained here? I close in 5 seconds. And the correct answer is not B, it's not the majority vote, is C, none of the above. This was a trick, but an important one. Here we have two different LANs, a red and a green one. Right? A has a packet to send to C. Well, they cannot communicate at the MAC layer because they're in different LANs. They're on the same switch, but the principle of virtual LANs is they cannot communicate at the MAC layer. Yes? No, A doesn't know, but it knows that the IP address of C must have a different subnet prefix than the IP address of A.
Why?
Because they're on different LANs.
VLANs?
Yeah, a VLAN is a LAN. A VLAN is a LAN, it is physically on the same switch, but you have to think of VLANs as they are separated local area networks.
But you can do VLANs with the same IP network.
You can cheat. You can always have two separated subnets that have the same subnet prefix, in which case you will need to do another trick to make it work. But the correct and normal thing to do, if you do a VLAN, it is because you want those devices to be in different subnets. If you don't want them to be in different subnets, there's no point in making VLANs. So the correct mode of operation in this case is, well, there's not just a switch, hopefully. If you have just a switch here that is performing only layer 2 switching, the red and the green cannot communicate. Perhaps that's what you want. You have two completely separate systems that should never communicate. If you want them to communicate, what do you need in between? You need a router. That's the principle of the internet. So you need a router that is both on the red and on the green VLAN. So the communication will be, A analyzes the IP address of C. It's not on link with me, even though it's physically on the same thing, but it's not on link. Therefore, I will send to the default router, which is here. Of course, very often, if you buy Cisco equipment, for example, S1 and R will be in the same box. So you will have a box that is called a combined layer 2, layer 3 switch that will perform both the VLAN function and the router function. But must not be this way. You could have boxes that are separated. Of course, you can cheat, you can do things differently, and we'll see an example a bit later. You could have two things that are not on the same subnet, but still believe they're on the same subnet, or vice versa. But if you violate one thing, you need to violate another one too, at least another one to compensate for the thing that will not work here, a bit like we've seen with NATs. A bit of terminology to conclude. This is what we have seen of bridges or layer 2 switches. Repeaters we've seen are physical layer devices. Let me skip this, which is bridges are typically used today to build wired infrastructure, but also to build wireless infrastructure indirectly. For example, this is the typical way of constructing a Wi-Fi network. That's the way we have in EPFL, the way we have also in the dedicated network, the TCP-IP SSID that we use for programming labs and other needs. So the typical way is you have a Wi-Fi base station that, if you have just one, then that's the end of the story. If you have several of them, they are typically connected by Ethernet. And the interconnection between the two is using a bridging function, so that if A sends to D or if A sends to F, as long as the network is not too large, this is considered as one bridge network. If the network becomes larger, you will separate it into subdomains. This is what is done at TPFL. At TPFL, there are above 1,000 base stations, so this is a large network, and structured into subnetworks that uses virtual LANs, as we have discussed before. Other than that, it's business as usual. So this base station has both Wi-Fi antenna and an Ethernet socket in the back where you can plug your Ethernet cable. And we can think of it as a bridge between Wi-Fi and Ethernet. Both are MAC layer stuff, so we can bridge between Wi-Fi and Ethernet. For example, if A has a packet to send to D to them, then they should be in the same subnetwork. A will send to the MAC address of D, and then there will be a spanning tree of the different base stations. The Ethernet might be a single cable, or most probably there is an Ethernet switch or several Ethernet switches, and a spanning tree will be built over which A first will broadcast the packet to D, and all the bridges on the way will learn the addresses. That's the classical bridging function, and this is what is typically deployed in all Wi-Fi environments. You might be confronted once in a while to various tricks. Here is one of the tricks that's played by Wi-Fi. The normal way of interconnect Wi-Fi base stations is by a cable infrastructure. But sometimes you see places where they are interconnected by Wi-Fi links themselves. So here there is the base station M1 that is used to give access at some point. And then we can connect M1 not to a cable, but to another base station M2. So it's a kind of what is called range extender. And the base station M2 can be connected to M3 and to M4 by Wi-Fi. It is usually a very bad idea. Usually the performance is very bad when you do that, because this is a single collision domain, but worse, when a packet from A to B is sent, A is sent to the base station here, which makes it impossible, for example, for M2 to communicate with M1 while doing that, because the base station here is M1 is at the center of a certain range. Furthermore, when the packet is forwarded to M2, it is resent by M1. But because the sending is typically creating interference in all directions, while M1 is forwarding the packet to M2, all this cell here cannot send. So there is a busy medium here, so this computer and that cannot send while M1 is busy repeating. And similarly, M2 will repeat, so a single packet will be repeated a number of times, which will create a number of collisions. So if there is a lot of traffic going from here to here, which is typically the case, typically this is connected to the internet, so all traffic goes along the hallway, so any packet is sent a large number of times, which dramatically decreases the performance. But it's cheap and it works well with if you don't have much traffic. So it's used. Now there is a concrete problem, that is normally this is a MAC layer switch system, so all those Wi-Fi base stations act as bridges. That's the principal intermediate system of layer 2 is a bridge. Now, when the packet is repeated from M2 to M3, right? If we apply the bridge principle, the source MAC address of the packet, of this packet, should be A. You've seen that bridges are transparent. When they repeat a packet, they don't change the source or destination address. In the same way as when a router forwards an IP packet, it doesn't change the source or IP destination address. The source is the very source of the packet, and the destination address is the final destination. Here the same is true. So this packet here will have source MAC address A and source destination address B. Now, the way the Wi-Fi shared medium access works is that it requires the MAC addresses to be used to know who should receive the packet. So in fact, this packet is sent by M2 to M3. So the protocol, the CSMA CD type of, or CA type of protocol that there is here, requires at least, for example, that the destination address, that there is something that identifies that the packet is for M3 and not for M1 or M4 or anybody else. If we don't have this information, because this is a broadcast medium, M1 and M3 will receive the packet and both might decide to receive it. Therefore, in Wi-Fi, there are additional MAC addresses in the header. There are up to 4 MAC addresses in a Wi-Fi header. The main 2 addresses are the source and destination, and then there are the transmit access point MAC address and the receive access point MAC address, which will be used in a case like this one. When M2 forwards this packet, it will use as transmit access point MAC address M2 and receive access point MAC address M3. Therefore, if you do Wireshark with Wi-Fi, you might see up to 4 MAC addresses in Wi-Fi headers. But this should not confuse you. I mean, the main addresses are the source and destination address. Those transmit and receive MAC addresses are intermediate addresses that are required for the operation of the collision resolution protocol. Remember, with Wi-Fi, there is an RTS and a CTS that is sent. RTS means ready to send. So when M2 sends a packet, this packet, you will send a packet to M3 to indicate to M3 that it has something to send to it. And M3 will need to forward it with a CTS to clear the space around it. And for this operation, we really need to be able to address M3 from M2, for example. This is why you will see such things. Yes? They are not changed. The source and destination addresses, the source and destination address do not change, but those addresses change on the fly, of course.
For example, if there is a chain of...
Yeah, like here, when M3 will send to M4, those two addresses will be M3 and M4. So this is a local address, group of addresses that's used to access the Wi-Fi link here. Sometimes, in particular in industrial environments like smart grid or factory automation or autonomous vehicles, you find things that are called non-routable protocols. The only difficult thing is to decode the terminology, which is not always very clear. A non-routable protocol means a protocol that doesn't have a network layer. Remember, if you have a small network, you can use the MAC layer only to communicate. So if you have in a room like this one some equipment like this camera, my microphone, and a number of things, they could communicate only at the MAC layer. It's a bad idea to do that because we probably want to use sockets and TCP-IP for communication. But some protocols were done either on purpose without using TCP/IP for reasons, typically because they're very, very simple and they're implemented on a very simple processing devices, PLCs, and not real full processors, or because they are very old and they were done in an environment where TCP/IP was not used. So that means, for example, inside an electrical substation automation system, PMU can stream data to a PDC, so a sensor can stream data to a database that collects all the data using protocols like Goose, SV, or others that are traditionally, typically at the MAC layer. Of course, it works only if you expect to deploy your things in a very small environment that exists. And they're called non-routable because there's no router in between. Doesn't mean you cannot route it, but it just means there is no concept of IP layer in the software here. More and more, such protocols are being transformed to be routable. So instead of using something that writes directly on the MAC layer, what you would do today is to write on UDP. So you would do a UDP application that would send to this guy, but there are some drawbacks. What are the drawbacks of, what is the benefit of not having IP? Has lots of drawbacks, but what is one benefit? Yeah? Security, that's one, security by obscurity, that's one of the principles. It's very hard for an attacker to access these machines if it really has no IP address, right? You will have a hard time accessing it from the outside. You need probably to take control of one of the computers and talk to it, but at the IP layer, you will not be able to access it. Yes?
Higher throughput?
Higher throughput, perhaps, but I hope not. I hope that the switch here, whether it's layer 2 or layer 3, would be able to process packets at the same speed. We save a bit. We save the IP header, but probably this is not a significant gain today. Yes? Simplicity. Simplicity of what? Software simplicity. I would claim that's the other way around. If you want to program a simple thing that forwards data from here to there, I guess it's much simpler to use sockets with UDP than to do it on this exotic thing that will probably not have a very sophisticated programming environment. Yes? By?
Binary size, if we have not a large amount of memory to implement the network.
Yes. So typically this is done if it's probably not simpler for the programmer, but it can make a program that is much shorter in footprint. So if this device is not a microprocessor, but a very simple device on which you have to, or FPGA, or you have to code everything manually, then you don't have an operating system that gives you support with sockets, then it might be simpler to do this. Another reason is also you don't need to allocate IP addresses. You don't need a DHCP server, you don't need all that stuff. All the MAC layer stuff only needs the information of the MAC layer. Now you will need a mechanism to discover what is the MAC address of those devices. Let me skip this. So let's do a break now, and after the break we will conclude with the security aspects of the MAC layer and start the transport layer. So we resume in 13 minutes.